Okay, I hope the slide is visible to you now. Can you please confirm somebody?
Yes, sir.
Okay, thank you. We'll get started right away. Okay, this class and the next class will be focusing on what is known as the application of Newtonian theory for hypersonic flows. This somewhat peculiar combination because Newton absolutely didn't have any idea about velocities which are higher than sound velocity. But then there is an application for a theory that he proposed for the flows that he is familiar with, like regular water flows, etc., to an entirely different field, that is hypersonic flow. So what we are going to try examine here is what is Newton's theory and how it can be applied to hypersonic flows, and why is that it becomes sort of surprisingly applicable to hypersonic flows. And we will also touch upon some of the applications of it, how we can make use of them in hypersonic flows. So that's a agenda for this session, and probably in the next one also. Now, before I get into that, I just want to announce that I was sort of lagging behind in uploading the PPTs, but as of now, I guess I'm up to date with all the PPTs that we have, all the sessions that we have covered so far. I have uploaded the PPTs onto the MS Teams files folder. So I hope they're all accessible to you now. And part of this today's class, I'll utilize for assigning some tasks team-wise. So we may stop the lecture a bit early, but then we'll utilize the remaining time to explain what is going to be the what I would call as the first assignment to be submitted by the various groups. Group 1 already had a presentation, so I'll be giving the problems for the remaining groups today. Okay, now let's start. The key issue here, actually not in this topic, but in several sessions that we are going to have, that is in the major chunk of this course, is surface pressure distribution. That is, when you have supersonic flow, we are particularly interested in external aerodynamics. And in external aerodynamics, as you always know from your aerodynamics course onwards, one of the key factors is how is the pressure distribution on the body, or what is the result as a result of the flow past the body, how is the pressure getting distributed. This is basically, this pressure distribution is what we eventually make use of to calculate the drag and the lift, etc. So all the aerodynamic parameters, force related parameters, are dependent on estimation of the pressure distribution on the surface. And this is exactly where we are going to make use of Newton's theory in hypersonic flow. So as I mentioned, the match of Newton's theory with supersonic flow is sort of a surprising combination, because I wouldn't think that Newton had even dreamt about any fluid flow higher than the velocity of sound. I don't know whether even the velocity of sound as a fluid flow parameter was visualized at that point of time. Anyway, that's immaterial. But the theory that he proposed for regular fluid flows has a surprising application in hypersonic. In fact, even in regular flows, that theory is practically not of great value today, because that's the reason we don't use that quite often, because it's just an estimation, and many of his assumptions do not hold for regular flows. So though it was applied for, say, liquid water jets, etc., the real application of them to some to a great extent is limited to hypersonic flow applications. Okay, so that's what we are going to look at here. And this is again, I guess I have mentioned 2 classes back that our initial discussions are going to be focused on inviscid flows. So in inviscid hypersonic flows, how we are going to use the Newton's theory and how is it, what is the extent of utility of it, and what are the further developments of it is what we are going to see. Now let's come to this Newton theory. It's fairly simple actually. Considering the kind of objective that it has, the formulation of the theory is quite simple. Newton probably was always obsessed with momentum and force and rate of change of momentum, etc. So he extended all that to fluid flows also. So Newton argued that when a fluid with some velocity impinges on a surface, the interaction can be considered as a series of particles, fluid particles striking the solid surface. A series of fluid particles. The moment you say particles is more like a Lagrangian approach, right? That is, you consider them having a finite momentum, a direction, velocity, etc. So he considered them as a group of particles hitting on a surface. And based on this, he proposed that during the, by the way, in fluid mechanics, have you come across Newton's theory? Probably not. Can you, somebody please respond? If you have, then I don't have to explain much about it. So have you come across Newton's theory in fluid mechanics, in force calculation? Answer,
No,
please.
sir.
No. Okay. So we'll start from the scratch. Actually, it's not too complex, as I mentioned. Basically, so he argues that when the jet is hitting the surface, now I'll try to point out the image. When the jet on the left hand side, the one that I'm referring to the left hand side figure now. There is a jet which I'm 1 second. Yeah. The direction of the image, that is the V infinity, the free stream velocity hitting an inclined surface. So you can imagine that you have a flat plate which is kept at an angle theta. So the free stream velocity, free stream jet of fluid, could be air or liquid or water or gas or liquid, anything, is hitting the surface. So please remember that the moment we say it's at an angle, we can consider a normal direction. That is, the velocity can be considered to be having a normal component. Maybe I'll just call it as V infinity n. That is a normal component of velocity, and a parallel component, a tangential component, maybe V infinity tangent, etc. You can consider it to be composing of 2 components. So what Newton said is that, so similarly, since I am resolving velocity, I can resolve the momentum also. So what Newton argued that during the collision, momentum in the normal direction will be lost, and that in the tangential direction will be conserved. That is, as an impact, as a result of the impact, the normal component of momentum, that is the momentum that is resolved in a direction at right angles with the impinging surface, will be lost. So the fluid will lose its normal component of momentum, and at the same time, the fluid flow will become, after impinging, it becomes parallel to the surface. That's observation also, as we know. After it hits the surface, it becomes almost parallel to the surface. So what do you mean by parallel? A direction that is tangential. So Newton assumes that in the tangential direction, the momentum will be conserved. So which means that let's go to the right hand side image, in which the flow direction V infinity is shown, the projected area a sine theta, right? But this angle is theta between the component and the surface. So the projection at right angles, that is the normal area, that is a sine theta. So we have the velocity v infinity hitting or covering a normal surface as of normal component of the surface area, which is equal to a theta. Now let's go to the application of this to the I will just come back to the derivation, but for a moment I'll just pause from here and I'll just take you to what do we mean by this in hypersonic flow. We'll come back to the derivation, but I want you to keep the hypersonic application in mind. You have a flow which is coming at, say, here I've shown a very high velocity, uh, 32, Mach number 32, which is in re-entry vehicles, etc. It's not unusual. So the free stream Mach number is 32, and we are considering a sharp cone, a reasonably sharp cone. The included angle is 10 degrees. Okay, so in the oblique short terminology, we have this angle as theta and the wave angle as beta. And this can be shown, I mean, from the tables, etc. You can get the value of beta easily as 12.3 degrees. We know that if you know Mach number and theta, we can calculate the wave angle using the chart of the cables. Okay, so this comes out to be 12.3 degrees actually. Okay, so now, so please keep this in mind. That is a flow hitting an inclined surface. Okay, now let's get back to the derivative. So this is going to be one of the applications. Okay, so I just want you to keep this in mind when we discuss the derivation of the Newtonian theory. The derivation is just a couple of steps actually, so it's not complex. Again, you have the incoming flow. You have the incoming flow, you have the inclined plate, you have the angle. So you have the V infinity here, you have the tangential component, you have the normal component. Now let's see how we formulate it. The mass flow rate is in the projected, based on the projected area, the mass flow rate is rho V infinity A sine theta. Rho V infinity A sine theta. Why is it a sine theta? Because we are considering projected area in the normal direction. Okay, so in the absence of theta, say suppose that you had a jet coming here, and if it was I'm sorry, suppose that you have a jet coming here, and if the plate were kept at 90 degrees with the jet, then obviously it is going to be rho a v, because sine theta is 1. So here we have a non 90 degree right angle inclination of the plate. So that's why we put it as rho v infinity as sine theta. Now, then what is the rate of change of normal momentum? Is the initial momentum minus the final momentum. Final momentum, Newton assumes that after it hits, the normal component of momentum is 0, which means that the rate of change of momentum in the normal direction is nothing but the initial momentum, because final momentum is 0. Now, what is initial momentum? It's mass into velocity. What is mass? Rho infinity v infinity a sine theta, which we have seen first. So we have it here. That multiplied by, now we are talking about normal component of momentum. So we just take the normal component of velocity. So mass multiplied by the velocity. So rho v infinity a sine theta multiplied by v infinity sine theta is the normal component of momentum, or rather the rate of change of normal component of momentum, which is nothing but rho infinity v infinity squared a sine squared theta. So now obviously this can be considered as considered to be equal to the force, right, by the second law. The rate of change of momentum is equal to force. So the normal component of force can be equated as F is equal to rho infinity v infinity squared a sine squared theta. which means F by A, which is the pressure, right? We conceptualize pressure as acting on the normal to the surface, right? So F by A, which is the pressure acting on the surface, F by A, right? That can be equated as rho infinity V infinity squared sine squared theta. Okay, so that gives us an expression for pressure. Now, in fact, this pressure, keep in mind that I guess Newton's argument stops here, but then the this pressure that we are talking about is, or this force that we are talking about is purely due to the impingement. But the main flow, as we know, has a static pressure anyway, which means that if you want to actually get the total pressure, the net pressure on the surface that the flat plate would feel, for that you need to add both the free stream pressure and the static pressure, which means that the net pressure that will be you should add the free stream pressure as well as what is calculated because of the impingement, right? In other words, the pressure on the surface, keep in mind that our focus is on the surface pressure distribution. So surface pressure would be the free stream surface pressure, which was always there, P infinity, plus what we have just calculated because of the impingement. Okay, P infinity plus the pressure, the force or the pressure due to the force of impingement, which is as per Newton's theory. This happens to be rho infinity V infinity squared sine squared theta. Okay, which in turn means that P minus P infinity. I'm just taking both the pressure terms to the same side. P minus P infinity is equal to rho V infinity squared sine squared theta. Or in other words, P by P infinity divided by half rho V infinity squared is equal to 2 sine squared theta, right? Just combining it in such a way that we can define or we can relate it to the definition of CP. CP we had discussed in the previous class. We have also looked at that form using Mach number. Anyway, P minus P infinity divided by half rho V squared is the familiar definition for pressure coefficient CP. So in summary, CP can be expressed as 2 sine squared theta. 2 sine squared theta. Now, please note that there is no velocity term in that, which means that the pressure coefficient is independent of Mach number and velocity. Okay, so if I were to extend that into supersonic hypersonic flows, then CP can be expressed as something which is independent of Mach number, and it's only dependent on the that is pressure coefficient. Please keep in mind, we are not talking about the pressure. We are talking about the non-dimensional parameter, that is with the with the division of half rho v squared, half rho v squared. Yeah. So the non-dimensional parameter Cp depends only on theta. It doesn't depend on the free stream velocity. Okay, so this is what the theory that is put forward by Newton. Okay, I'll pause here. We will see how we apply that to hypersonic flows. But if you have any questions, please. No. Okay, so we move forward. Now, so this says that as per Newton's law, and straight Newton's theory, the pressure distribution can be calculated just based on the local deflection. Now, what is local deflection? The angle theta. That is how much the flow is inclined with respect to the flat surface. Now, this though the derivation is only is done or explained for flat surface, this can be applied for in a similar way. It can be applied for pointed bodies with a little bit of curvature also. So as you can see in this picture, the theta that can be measured as a main direction and the tangent at that point. And we can apply it the same way. So in hypersonic flows, if we were to apply this, we will consider the mainstream direction where the flow is coming with a very high velocity, with a high Mach number, and we'll be considering theta can be actually the local deflection angle. So at any point when I'm considering the pressure distribution, I will consider the angularity at that point. So it can be calculated, and if required, can be integrated over, etc., or it can be approximated locally, or whatever way. That depends on the degree of extent of accuracy that you want. So it can be considered as it can be applied this way to the hypersonic flows. And now the same theory actually extends and goes on to say that the flow, when you have this kind of an approximations, that is when you say that on impingement it loses its normal component, and the tangent, everything becomes tangential, the whole the flow becomes fully tangential. It also implicitly says that it cannot curl around the body, which in turn means that the force is experienced only on the face where the flow is hitting. Since it cannot curl around the body, the rearward surface is not exposed to the pressure at all. So you can, it is a natural extension of Newton's theory to say that Cp on the other side is 0. So the facing side has the value of Cp, which we estimated as 2 sine squared theta, and the other side is the flow cannot reach there because it just becomes tangential and doesn't have momentum to curl around. So the other side has Cp equals 0. So that's what is schematically shown in this picture. Now, let's take it to hypersonic. So I just mentioned that it can be applied to hypersonic flows. But then the question is, why Newton's theory is applicable to hypersonic flows? So that is, in supersonic flow, you don't find much applications. Even in regular flows, incompressible subsonic flows, nobody talks about Newton's theory nowadays. So why is that we are extending it to hypersonic flows, or why is that it suddenly becomes applicable at hypersonic flows? There are a few reasons for that actually. I would consider that whatever I have listed here to the 3 points, they combine, the combined effect of these points is the defense for the argument of extending Newton's theory for hypersonic flows. First is, there is no upstream streamline curvature. That we know that, because that applies, that's not specific for hypersonic flows. Even for supersonic flows, we know that when the flow hits, then only the change or the transformation, as long as we are talking about a surface like this, pointed surface, the curvature or the flow turning happens after the flow hits the surface, right? There is no the streamline turning a priori, unlike in the case of subsonic flows. So, which means that this is applicable to, this is where actually Newton also started off with. So Newton's argument was that the flow hits and then flows over it. I repeat that, flow hits the surface and then becomes parallel, becomes almost tangential to it. So to that extent, this is here true in our case also. The flow turns only after hitting, and there is no free streamline. There is no streamline curvature a priori. That's one. Second is, as we have seen here, Cp is independent of Mach number. So Cp is independent of velocity, and hence it's independent of Mach number as well. Now, this Mach number independence in hypersonic flow, this we are going to see a few sessions later. Actually, we will have some discussions focused on Mach number independence, where we will show that in hypersonic flow, that is when Mach number increases beyond 5, etc., some of the phenomena become independent of, some of the flow properties, etc., tend to become independent of Mach number. So that's basically what is called as Mach number independent, and Cp is one of them. So we will going ahead, we'll put that more formally with more sound theoretical foundation for it. but we will discuss Mach number independence. I'm just taking that concept here, advancing that here, and just stating that in hypersonic flow, many of the non-dimensional parameters tend to become independent of Mach number. And this is exactly what Newton also says. There is no dependence of Mach number on the pressure distribution. Again, I repeat, Mach number as a parameter was not defined at Newton's time. Probably the concept of supersonic flow itself was not there. Okay, not, I don't know. Probably if they even considered compressible, incompressible, etc. So, I'm just extending the terminology to the theory. Okay, so it's not that Newton argued this, but what we see today is that the Mach number independence is in line with what Newton happened to assume in the case of normal fluid impact. So that is another thing which is in favor of hypersonic. Now please note, the first one is true for supersonic and hypersonic flows, but the second one is true only for hypersonic flows. Okay, the first one, that is the no flow turning, is applicable to supersonic and hypersonic flows, but the Mach number independence, we will see that later, that it becomes real, or it becomes it tend to become accurate only for hypersonic flows, not for lower Mach numbers. Okay, so that's why we don't talk about. So that's the second point actually eliminates the applicability of Newton's theory to supersonic flows. Now the third one, a near tangential flow over the surface due to the low wave angle. This is also important. Actually, it's very important, and this is particularly applicable for sharp bodies and hypersonic flows, where we will see more applications for Newton's theory. That is for sharp edge bodies. That is when theta is low and when omega and beta is low. Now let's try to understand this a little bit more. What do we mean by near tangential flow over the surface due to the low wave angle? I'll try to explain that a bit more, but so far if you have any doubt, you can ask me, or I can even postpone this discussion to next class. I guess, yeah, I guess I'll take that in the next class. So what do I mean by this near tangential flow, and why do we say that we have low wave angle and the flow can be considered tangential? Because that requires a bit more detailed explanation possibly. Not only that, I need to spare some time to explain the assignment. So I stop here. If you have any questions, we'll take that first and then go to the assignments. Now questions, and we'll go to the assignment description. As I mentioned, I've listed some tasks which should be presented. You should do a little bit of work on them and present them. Presentation should not take more than 5 minutes or so, because we need to cover all the groups. May not be in the same session, but we'll distribute it accordingly. I mean, depending on the time. But I request that all the groups. Now, group 1 has already done a task, so I exempt them in this series. But everybody should be part to the presentation, should be part to the discussion, etc. Now, what I suggest is what I want you to do is you submit the presentations a priori. So today is Thursday. Yeah, by Tuesday you should see all these four teams, 2, 3, 4, 5, should submit. They should upload their presentations in MS Teams. Okay, so I guess you have an assignment folder or something. So probably you can upload them all in the assignment folder. So please take that as the deadline. That is, by Tuesday you should have uploaded the presentations on this. Now, when do you present? That can be starting maybe I guess Tuesday itself we have a class, so maybe starting on Tuesday itself. So group by group we can have the presentation, 1 or 2 groups max in a session. So we will spare time after the main lecture. We'll have some time that is left for the presentations. So the earliest can be Tuesday, and then we can have 1 or 2 on Tuesday, and then 1 or 2 presentations on Tuesday, and then the subsequent sessions also. 1 or 2 again, depending on the time that is available. Okay. And I don't expect the presentation to take more than 5 minutes. It's not too many things to talk. Maybe just a couple of slides and a few graphs. But then we will leave some time for the presentation as well as for the following discussion. Okay. So that's going to be the pattern of the scheme that we follow for the presentations. Now, I'll try to explain the first assignment to group 2. By the way, group 2, everybody is present now. Let me, yeah, group 2. Lakshmi Shivakumar, Naresh, Nitin, Nibeta, and Pavan. All of you are around? Please respond. You want I'll call one by one, please.
Yes, sir.
Yes, sir.
Yes, sir.
All of you are there, right? 1, 3, 4, 5. Yeah, all the 5 are there, right?
Yes, sir. Yes, sir.
Yeah, this is again this derivation that we have done already. B by theta equal to gamma plus 1 by 2, which refers to the ratio of wave angle to the cone angle, or whatever the deflection, the corner angle. That's a ratio, and the relation is for hypersonic flows. And we know there are some constraints when we apply this. So what we are going to do here, or what we are supposed to do here, is consider the following two values for deflection angle. Theta 1 equals 5 degrees and theta 2 equals 15 degrees. So you are going to take two cases. You can consider the angle theta, the compression angle theta, for the first case as 5 degrees, which is a fairly sharp one. And the second one is a relatively blunt one, 15 degree. Okay. Now for both theta 1 and theta 2, calculate the wave angles based on hypersonic limit. Okay, so you have the B by theta relation here, quite straightforward. So you use gamma equals 1.4, calculate the beta value for both of them. Now, I want you to also do the calculation making use of the oblique shock formula, which we have used in compressive fluid flow. So actually, you can use this particular link. This is, in fact, this is for the entire class, okay? Because we will be using this link for quite often for whenever we need to do any shock-related calculations. This is Virginia Tech. I'm sorry, it's not, the hyperlink is not inserted here, but that you can find it out. And once I upload it, you can go through it and get that link. It's a very convenient, intuitive online tool. Probably you would have seen it already. Virginia Tech, where you can calculate the ratios across shocks, oblique shocks as well as normal shocks, and also Prandtl-Meyer expansion, etc. You can just see that. I mean, it doesn't require any training, etc. So just by seeing that, you'll be able to do that. So you make use of that table, that site, online tool, and then calculate the free stream Mach number for free stream Mach numbers. That is the wave angles you use for this for these two combinations. You use M1 equals 2, M1 equals 12, M1 equals 24, and M1 equals 30. That is for different Mach numbers. 4 different Mach numbers which range over 2 to 30. Now, the importance of this range is we are starting from early subsonic and then going to a high hypersonic. Okay. So for all these, you calculate the wave angles, that is beta, for the given two thetas based on the full oblique shock relations without the hypersonic approximation. Now I want you to make a comparison, make an appropriate tabulation and plot. Okay, so you can use Excel sheet, quite convenient actually. It wouldn't take much time. So you just put all the values in table and then plot them. Make a graph, a convenient graph that you can explain the difference or the comparison between them. Compare the values that you get for beta for all the values B1, beta 1, beta 2, beta 3, beta 4, because we have 4 Mach numbers. Okay. And then calculate them or compare the results with the hypersonic limit b by theta. B by theta equals gamma plus 1 by 2. So that gives you a value of beta. The full shock calculation also gives you a value of beta. I want you to compare that. Okay. And then summarize your observations. So that's important. The fifth step, you should summarize as the observations inference the validity and applicability of the hypersonic limit approximation for wave angle. So then you should tell us where is actually it is applicable. That is, what range of thetas or Mach numbers is this this is applicable. This b by theta hypersonic limit is applicable. Okay, so you are going to basically compare it, compare the values with and without hypersonic application, hypersonic limit application, and then see and going to recommend, yes, where can I reliably or reasonable accuracy, with reasonable accuracy, I can apply the hypersonic limit. Okay, so once you start doing it, you will get more clarity to it. But then I would like you to do this, present the results, and explain your findings. That's about group 2. Is that clear? You have any question, you can please ask. Group 2. No. Group 3. There are two relations. Again, a similar one. You have rho 2 by rho 1, which we have defined for oblique shock. Oblique shocks. And we did it for hypersonic limit. We saw that it becomes gamma plus 1 by gamma minus 1. It's independent of Mach number. Now, at the same time, on the right hand side, you have the rho 2 by rho 1 relation for a normal shock. Normal shock. Okay, this is from compressible flows. We didn't do the derivation here, but we know where it comes from. Okay, so rho 2 by rho 1 is a function of the upstream Mach number, gamma plus 1 m1 square divided by 2 plus gamma minus 1 m1 square. Okay, the on the left hand side you have the hypersonic limit, which we derived for oblique shocks. It's similarly applicable for normal shocks also. So on the left hand side we have the hypersonic limit. On the right hand side we have the general relation rho 2 by rho 1, which can be used for any Mach numbers. Okay, so I want you to do a similar one as I mentioned earlier, but I want that comparison to be done rho 2 by rho 1 across normal shock for 3 values of gamma: 1.1, 1.2, 1.4. See, we had discussed about chemical effects in dissociation, etc., in hypersonic flows. So in hypersonic flows, it's quite often it may happen that gamma may not be 1.4. Gamma can have other values. So that's what we are trying to highlight here. You use 3 values of gamma: 1.1, 1.2, 1.4, and over a range of Mach numbers 2 to 24. Now I have not listed what are the Mach numbers, but you select whatever you want, but it should be a sufficient number to have the plot, and it should be ranging from 2 to 24. Actually, in Excel sheet, you don't have to do the whole thing manually. Once you have a set of calculations, you can do only the table, the rho 2 by rho 1 using normal shock, you may have to take manually. Even that is quite straightforward from that particular interface, the web portal of VT, which I just showed. So you just make tabulated for Mach numbers. Mach number can be like say 2, 3, 4, or 2, 4, 6, or whatever. But there should be sufficient numbers between this range of 2 to 24. and then plot the variation on a row 2 by row, row 2 by row 1 here. Okay, it's wrong. Row 2 by row 1 on y-axis, row 2 by row 1 on y-axis, and Mach number on the x-axis. So you will have row 2 by row 1 on y-axis, Mach number on x-axis. And then I want you to compare how the values compare with the hypersonic limit. And again, your observations on the applicability of the hypersonic limit for row 2 by row 1. You should tell where is it, or how it becomes applicable, or when it becomes applicable, and why it becomes applicable. Okay. Any question there? Group 3? No. Group 4. Now, here what we just discussed was row 2 by row 1 and along with the hypersonic limit. Group 4 has a similar task, but this is with focus on P2 by P1, the static pressure ratio. I have not put the ratio here. We have discussed it. So you can just take the P2 by P1 ratio for a normal shock. So don't worry about the wave angle, gamma, etc. You can use the P2 by P1 for normal shock. You can get it from compass anywhere. The relation is quite easily available. Draw the P2 by P1 with Mach number, the normal shock relation. Use that, and again repeat the calculation for gamma 1.1, 1.2, and 1.4, and plot the variation with P2 by P1 on y-axis, Mach number on the x-axis, and comment on what is given the last. You based on the graph, say whether there is a limiting value for P2 by P1 as m tends to infinity. Now, if it is there, state it. Otherwise, find your observations and probably define what you are going to see as the observation in the graph. Okay.
Okay, sir.
Yeah. Next one, group 5. This is about the design of a scramjet. We had briefly discussed about it. That is when you have a scramjet, it's aimed at operating at high hypersonic Mach numbers. The present designs which are in research, when we say it's something like 10, 12, etc. We consider a Mach number, a scramjet to be operating at 10, Mach 10, okay, cruising level flight at Mach 10 at an altitude of 15 kilometers above sea level. 15 kilometers, which means that I want you to find out the static pressure and static temperature, whatever is required here. The atmospheric properties that you take should be at that level, 15 kilometers above the sea level. Now, assuming adiabatic compression at the intake, that is, there is no heat radiation, heat loss, calculate the resulting temperature Tc to the combustion. Now, we know that the flow comes in at Mach 10 at the intake, but it is decelerated before it goes to combustor. So yeah, it is decelerated to a subsonic value, so supersonic value, not a subsonic value. Now the question is, what should be that supersonic value at the inlet to the combustion chamber? I want you to examine this in the range of starting from, say, I'm using Tc to the combustor inlet temperature, static temperature. Static temperature at the inlet to the compressor combustion chamber is Tc. Similarly, Mach number to the inlet to the combustion chamber is Mc. Now, I want Mc to be, you consider it is 1.5 and in the range of 1.5 to 5. So you can take maybe 1.5 to 2.53, etc., etc. Convenient intervals. Okay. But I want you to start from 1.5 and 5. What do I mean by that? That is, you consider the first case would be the Mach 10 flow is decelerated to 1.5 before it goes into the combustion chamber. The last case will be Mach 10 flow is decelerated to Mach 5 before it goes into the combustion chamber. I want you to calculate the resulting Tc, and that's quite straightforward, right? We know the it's adiabatic compression, so T naught can be assumed to be constant. T naught you can calculate upstream. You can assume that to be constant all through. So I want you to calculate Tc based on Mc. That's all. Now you make a plot of Tc versus Mc. Okay, and then make a recommendation as to what value of Mc you should be targeted in the design, and then justify the recommendation. If it is high or whatever it be, but you say why you say that, yeah, this is the better value for design. This is a better value for the design. Okay, and you can all through assume gamma to be constant and at 1.4. Okay, so This basically boils down to a given set of operating conditions, deciding what should be the inlet Mach number for the combustion chamber. But the 1, 2, 3, the last but one point is very important. When you make your recommendation, you should also say why you say that. Okay, so why is that? Say if you say MC has to be 4, then you should tell why 4. Why don't you suggest 5? Why don't you suggest 3? Okay, so that kind of a defense has to be there. I guess that's all for my side. So if you have any questions, particularly group 5, anything? If not, we'll stop here. But then I didn't. I checked with group 2. Everybody is available. I didn't check with the other teams. Can I quickly make sure that most people are around? Say Rajeshri is around. Upload. Sorry, please unmute and tell me. Rajeshri of group 3.
Sir. Yes, sir.
Renish. Renish.
Yes, sir. Yes, sir.
Patnaik, Sanjay.
Yes, sir, I'm
They-
here, sir.
Great. Yeah. Group 4. Sanjay Krishna.
Yes, sir.
Syamala. Syamala.
Yes, sir.
Yeah. Surya Prakash and Swaroop.
Yes, sir.
Both of you are there, right? I hope so. Yeah. Now group 5, Yuvraj. It's not there. Nagamala, Shashank.
Yes, sir.
Great. Roll number 54. I'm sorry. Sami was. Yeah. 54.
There, sir.
Yeah. Sahana, 61.
Yes, sir. Yes, sir.
So you know what is to be done. I request you to upload the presentation by Tuesday. Okay, in MS Teams, in the assignment folder. Okay.
Okay, sir.
Thank you. So we'll stop for the day. Thank you. Thanks to all of you. Bye.
Bye.
Thank you, sir.
Thank you.
Thank you.
Thank you.